Hello and welcome to this video lesson, which is the first in the equilibria and redox reactions section. The first video lesson here is on reversible reactions with specification reference 3.1.6.1. And our learning objectives for this lesson are, firstly, we want to know that many chemical reactions are in fact reversible. They go in two ways at once. Also, we want to know that in a reversible reaction at equilibrium, the forward and reverse reactions proceed at the same rate. And what that means is that for a reversible reaction at equilibrium, the concentrations of the reactants and products are the same. And that follows on from the forward and reverse reaction rates being the same. And also, we want to know and be able to use Le Chatelier's principle to predict qualitatively the effects of changes in temperature, pressure, and concentration on the position of the equilibrium. So let's get to it. But first, let's just finish off the lesson objectives. We've got a last one here, which is we want to know that a catalyst does not affect the position of equilibrium. It lets equilibrium be reached quicker, but it doesn't affect the position of the equilibrium. So let's start by considering this concept of dynamic equilibrium. And let's do that by means of using a reaction between hydrogen gas and iodine. Let's put that in the gas phase as well. And that's an equilibrium reaction, so we write our equilibrium sign here. And we are going to make a product called hydrogen iodide, which is also a gas. And what this means is that at the same time, there's two different reactions going on. We are reacting hydrogen and iodine to make hydrogen iodide. That's called the forward reaction because that's written in this direction. And at the same time, though, once hydrogen iodide has been produced, some of those hydrogen iodide molecules decompose back into hydrogen and iodine. They decide that they're not stable as hydrogen iodide, and so they decompose back this way. Some of them decompose and some of them stay as hydrogen iodide. So we've got two reactions going on at the same time. So let's write them out separately. Firstly, as we've written here, let's write down the forward reaction. So we've got hydrogen gas, and we've got iodine as a gas. Right. And the forward reaction there, we write it with an arrow this time. We're going to make two hydrogen iodide molecules. So that's the forward reaction, and let's do the backward reaction in green. So the backward reaction starts off with two hydrogen iodide molecules, and they split up to make one hydrogen gas molecule and one iodine gas molecule. And those two reactions are going on at the same time. So let's consider the first reaction here, the one in blue. And what we can see is that we're starting off with some hydrogen and some iodine, and we've got no hydrogen iodide yet. So under those conditions, the rate of production of hydrogen iodide is quite fast because we've got lots of reactants. Or we could say the rate of usage of hydrogen is quite fast because we've got a lot of hydrogen and we've not got much hydrogen iodide. So it's being used up quite quickly. And then as it's being used up, as the hydrogen is being used up, there's less of it left. And so there's less of it left to react. And so the reaction rate is going to slow down. So we can write that as a reaction rate versus time. So let's define our reaction rate as the change in concentration of hydrogen gas over time. That's just one way of writing our reaction rate. and that's versus time. Okay, so it's going to start off quite quick. So let's start it off up here. So it's going to start off quite quick, but then it's going to decrease, isn't it? It's going to decrease as our hydrogen decreases. As our hydrogen reacts, there's less of it left, so the reaction rate decreases. So we'll draw it like that. Okay, let's leave that for just now. Let's go over to the green side, where we're looking at hydrogen iodide. So as we said before, we've started with very little zero hydrogen iodide, and so the decomposition of hydrogen iodide to hydrogen and iodide is, by definition, is zero. But as the forward reaction has produced hydrogen iodide, right, then we've got some to decompose, and so the more that's being produced, the more that can decompose, and so the reaction rate can increase up to a limit. So in the same way, why don't we draw a little graph of that? So this is going to be our change in hydrogen iodide concentration over time versus time. And we're going to start at zero, like we said. It's going to increase quickly, but then as it starts decomposing, it is going to plateau off as well until it's steady. And so what we have here is, on the left hand side, we have our forward reaction rate. Let's call that forward reaction rate. And in green on the right hand side, we have our backward reaction rate. Yeah. And the way that I've drawn that, I deliberately drew it so that eventually the reaction rates will equal out. So we could draw it like this. Such that after a particular time, let's draw our dotted line down. After a particular time, the forward reaction rate is the same as the backward reaction rate, and that, let's annotate that little point in time there, that is when equilibrium is reached. Sorry, very bad writing, but hopefully you've got that. That's when equilibrium is reached, when the forward reaction rate is the same as the backward reaction rate. And that is dynamic equilibrium. But it only happens in a closed system. So what we mean by a closed system is that nothing can get in or out. If it's an open system, then some of your product will escape, and you'll probably never reach equilibrium. So we're talking about a closed system here, and so this defines a dynamic equilibrium. And one last thing to clarify is that if our forward reaction rate, which is the rate of change of concentration of our reactants, is the same as our backward reaction rate, which is the rate of change of concentration of our product, then if they're both the same, then by definition our concentrations are not changing. So let's just write that down to make it exactly clear. So at equilibrium, the concentration of reactants and products is constant. So next up is Le Chatelier's principle. You may have come across this at GCSE, but let's go into it in a little bit more detail. But first, a revision as to what it is. Le Chatelier's principle is here. I'll read it out for us and then we'll unpick it. So if a reaction at equilibrium is subjected to a change in concentration, pressure or temperature, the position of equilibrium will move to counteract the change. So that's what it says, but what does it mean? Okay, so let's unpick it. So there's three things we need to unpick. All right, the first thing is we need to understand the position of equilibrium. The second thing we need to unpick is move. So the position of equilibrium will move. And the third thing is change in concentration, pressure or temperature. Okay, so let's do it in that order, starting off with what we mean by the position of equilibrium. So the position of equilibrium is just the amount of reactants and products at equilibrium. So if we say the position of equilibrium will move, that just means that we're going to have, at equilibrium, we've got a certain amount of reactants and products that are, the concentrations of which are not changing. And if that position moves, it just means we've got a new amount of reactants and a new amount of products at the new equilibrium position. So because it's at the new equilibrium position, it's still at equilibrium. You have steady concentrations, but different concentrations to the ones before. So that is the position of equilibrium. And let's think about moving. So let's go back to our example. So let's explain moving. So if we have our hydrogen plus iodine example, going to hydrogen iodide. If we look at that example, if we say the position of equilibrium has shifted to the right, so shifted to the right means we've shifted in this direction, so I'll put it in quotation marks, shifted to the right, and that means more products and hence less reactants at equilibrium, at the new equilibrium, yeah? But if we say that it's shifted to the left, then the opposite is going to be true. If we've shifted it to the left, move to the left, of course that means we're going to have less product or more reactants at the new equilibrium position. So that's what we mean by move. And lastly, the green one, change in concentration, pressure or temperature. So let's try and find a space down here for that. So first of all, change in temperature. So if what it means is if we increase, let's say we increase the temperature, then what the equilibrium position is going to do is it's going to do the opposite. It's going to counteract the change. So it's going to, equilibrium position will remove the temperature. The equilibrium position changes to decrease the temperature. And by the same token, if we increase the concentration or the pressure, all it means is that the equilibrium position will move, so the amount of reactants and products will change in order to decrease the increase in concentration. So the equilibrium position, or the amount of reactants and products, changes to decrease the concentration or pressure. So that's Le Chatelier's principle, and what I'd like to do is like to go through Le Chatelier's principle in more detail now. So now we're going to have a look at using Le Chatelier's principle in a little bit more detail. But let's just remind us what Le Chatelier's principle is. We're going to leave that up there to just have it as a reference. So firstly, look, what we're going to do is we're going to deal with each of these as we go along. So first of all, we're going to do a change in concentration. Secondly, we'll look at in detail a change in pressure, and then lastly we'll look at a change in temperature according to Le Chatelier's principle. So first of all, let's consider what happens when we change concentration. So using a real reaction, then let's pick the sulfur dioxide reaction, where we start with 2 moles of sulfur dioxide gas, and that's going to react with a mole of oxygen gas, and that's in equilibrium with its product, sulfur trioxide. Okay, so those reactions are happening at the same time. You've got sulfur dioxide reacting with oxygen to make sulfur trioxide, but at the same time that's happening, you've got sulfur trioxide decomposing back into sulfur dioxide as the backward reaction. So let's use a table here to illustrate all the different ways that we can use Le Chatelier's principle. So on the left hand side, let's list out a few changes in concentration. And what we're going to do is we're going to look at what the equilibrium position does when subjected to that change in concentration. Okay, so firstly, let's assume that we increase the concentration of a reactant. Increase conc of a reactant. Alright, so our situation was at equilibrium, and then we went and made a change. Okay, we increased the concentration of a reactant. Let's say it was sulfur dioxide. What does the equilibrium position do? Well, it's going to move, i.e. it's going to change the amounts of reactants and products to counteract that change. Right, so what it's going to do is it's going to make more product. And in technical terms, we can say that is shifting to the right. So the equilibrium position shifts to the right. Alright, so it's going to go in that direction there. That's one change in concentration we could do. We could do the opposite. We could decrease the concentration of a reactant. So we could decrease the concentration of sulfur dioxide in a closed system at equilibrium. So what's the equilibrium position going to do then? Well, it's going to counteract that change according to Le Chatelier's principle, and counteracting that change in practice means that you're going to make more reactant. You're going to make more reactant. So in that case, what's happening is the backward reaction is happening at a faster rate. Okay, so we could say the equilibrium position shifts to the left. To reach a new equilibrium position eventually. Okay, so that's two of our changes in concentrations we could possibly do. We could also increase the concentration of a product. In this case, we've just got one product, sulfur trioxide. So if you added some sulfur trioxide somehow to our closed system, then our equilibrium position would alter. It would alter in order to counteract that change. So if we've added a product, what the equilibrium position is going to do, it's going to make more reactant. Right, and so we can say that the equilibrium position has shifted or moved to the right, or to the left. This should be this is totally wrong, isn't it? It's going to shift to the left in red. Sorry about that. Okay, so our last change in concentration that we would do is we could decrease the concentration of product. In which case, we're going to make more product to counteract that change. And making more product is shifting to the right. So the equilibrium position can be said to shift to the right. There we go. Hopefully that summarizes the changes in concentrations that are possible. And there's only 4. Because if you change one reactant, it has the same effect as changing a different reactant. So there's only 4 changes of concentration that you can do, and they are the 4 different responses that the equilibrium position makes in order to counteract those changes that we've made to the original equilibrium position. So on the last slide, what we dealt with was changes in concentration, and on this side what we're going to do is changes in pressure. Let's deal with that in some detail. So we're going to change pressure, and in order to do so, let's have a look at a couple of different reactions. One which we'll write in green, which we're familiar with. This is the sulfur dioxide reaction. So we've got 2 moles of sulfur dioxide plus a mole of oxygen, and that's in equilibrium with sulfur trioxide. Okay, that's one reaction we'll look at, and let's look at another reaction as well, and I'll explain why. So we've got some methane, and that can react with water as a gas, because we're dealing with pressure. So Le Chatelier's principle, as far as pressure is concerned, it just considers gases. And methane and water reactant would be in equilibrium with carbon monoxide and hydrogen. Okay, so the first thing to notice about these reactions is how many moles are on the left hand side and how many moles are on the right hand side. So let's count. For the green reaction, we have 3 moles of reactants. And 2 moles of products. Whereas for the blue reaction, the methane and water reaction, we have 2 moles of reactants and we have 4 moles of products. Hopefully you can see that. So there's a different number of moles on each side. In our green reaction, our sulfur dioxide reaction, we have fewer moles of products than reactants, whereas with our methane reaction, we have more moles of products than reactants. Okay, so the change in the pressure will affect these different types of reactions differently. So in the same way as we did with concentration, let's have a look at a table. Okay, so let's have a look at what change in pressure we might make, and in the same way what the equilibrium position does. Remember, equilibrium position is just the amount of reactants and products. So what it does when it's subjected to a change in pressure. Okay, so there are actually only 2 possibilities for a change in pressure. We can either increase it or we can decrease it, because both reactants and products are all mixed up in the same container, and if we're increasing the pressure of reactants, we're doing exactly the same to products and vice versa. So they're the only 2 possibilities. We can either increase the pressure or we can decrease the pressure. Okay, so let's switch to green and we'll deal with the sulfur dioxide reaction first. Let's deal with generically. So when we increase the pressure of a gaseous equilibrium, then the equilibrium position what it wants to do in principle is it wants to make fewer molecules. It wants to make fewer molecules, so then that can counteract the increase in pressure and decrease that pressure back to near what it was originally. All right, so in principle, the equilibrium position wants to make fewer molecules if you increase the pressure of that system. So what does that mean for the green reaction? Well, in order to make fewer molecules, you've got to move to the side of the equilibrium which has fewest moles. Okay, so we're going to shift to the right for the sulfur dioxide reaction, right? Because there are fewer moles on the right hand side and we want to make fewer molecules, so the equilibrium position is going to make more sulfur trioxide at the expense of the sulfur dioxide and the oxygen. Whereas for the methane reaction, which I'll write in blue, making fewer molecules means actually shifting to the left, means making more reactants, because there are fewer moles of reactants than there are products. Okay, so for the methane reaction, that means it shifts to the left. Okay, so hopefully that's clear. Then what we can do now is consider a decrease in pressure, just to make sure we've understood. So we've got a gaseous equilibrium with a mixture of reactants and products, and somehow we decrease the pressure. So we decrease the pressure. So the Le Chatelier's principle says that the equilibrium position will try and counteract that change. So it will try to increase the pressure. How is it going to increase the pressure? Well, it's going to make more molecules. So the equilibrium position is going to move, and in a way that makes more molecules. That's in principle what it's going to do. All right, but whether that shifts it to the right or the left depends on the number of moles of reactants versus products. So in the green reaction, the sulfur dioxide reaction, where we have more moles of reactants than products, that means we're going to shift to the left. Because by shifting to the left, we are using up a small number of sulfur trioxide molecules to make more molecules of sulfur dioxide and oxygen. So that makes more molecules by shifting to the left. Whereas for the methane reaction, the one in blue, making more molecules means shifting to the right, because that means we would use relatively few molecules of methane and water, and we would make many molecules of carbon monoxide and hydrogen. Okay, so it means the equilibrium position would shift to the right. There. And that is Le Chatelier's principle as far as changing pressure is concerned. So it's probably worth just being complete and saying, what about if there are the same number of moles on either side? In which case, changing the pressure will not affect the equilibrium position. Okay, now I think we can move on to temperature. So, using Le Chatelier's principle this time to look at what happens when we change the temperature. So let's have a look at two different reactions. We're going to have one, they're both equilibrium reactions, but there's one which is going to be exothermic in the forward direction and one which is going to be endothermic in the forward direction. So let's write them up here. So our sulfur dioxide reaction is exothermic in the forward direction. Okay, and our enthalpy change for that reaction is minus 197 kilojoules per mole. Okay, and just to clarify that reactions are always written. So if the enthalpy change there of minus 197 is given for the forward reaction. So that means in this case the forward reaction, this one here, is exothermic. And the other reaction that we'll study is dinitrogen tetroxide. And that's in equilibrium with 2 moles of nitrogen dioxide. And the enthalpy change for the forward reaction in that case is a positive 57 kilojoules per mole. Okay, so this forward direction is endothermic because it's positive, whereas that one the blue one was exothermic because our enthalpy change was negative. Okay, so in the same way as we've done with the previous two, we're going to have a look at the table, and we're going to have a look at what possible changes in temperature we could make. So our change in temperature is going to go on the left, and in the same way, what the equilibrium position does is going to go on the right hand side. Okay, so again, our reactants and products are all mixed together, whether they are liquid or gas, and so that means that we can only either increase the temperature or decrease the temperature, because we do the same to both reactants and products. So we can only have an increase in temperature or we can decrease it. So let's consider increasing the temperature first. Well, if we increase in temperature, what in principle does the equilibrium position want to do according to Le Chatelier's principle? If we are increasing the temperature of a system that's happily in equilibrium, then the equilibrium position is going to change to remove heat. We're increasing the temperature, so we're adding heat, so the equilibrium position is going to change to counteract that change, i.e. remove heat. So removing heat means we're going to get more of the endothermic. Reaction. Now, how we remove heat, of course, depends on the type of reaction, and that's why we're using two examples here. So let's consider first the exothermic forward reaction, i.e. the sulfur dioxide plus oxygen reaction in blue. So if the equilibrium position wants to remove heat, it's going to want to favour the backward reaction, because it's the backward reaction that is the endothermic reaction. So it's going to shift to the left. Because by shifting to the left, it's favouring the endothermic reaction. Now let's switch to the green reaction, the dinitrogen tetroxide reaction. Again, we want to remove heat, but in this case, it's the forward reaction that is the endothermic reaction. So we want more of the endothermic reaction to remove heat. So in which case we want more of the forward reaction. So that means more forward reaction means we're going to shift to the right. And both of those shifts involve favouring, let's write down here, favouring the endothermic direction. Okay, so that's dealt with an increase in temperature. Let's now do the opposite. Let's assume we've got an equilibrium mixture and we decrease the temperature. We remove heat from it. If we're decreasing the temperature, we're removing heat. So the equilibrium wants to do the opposite. So it wants to add heat. In order to add heat, what's the equilibrium position going to do? Well, it's going to favour the exothermic reaction, because it's the exothermic reaction that's going to provide that heat. Okay, now in order to add heat, each reaction is going to do it in a different way. So going back to our sulfur dioxide, our blue reaction, if we want more of the exothermic reaction, our equilibrium position is going to shift to the right. because it's the rightward forward reaction that is the exothermic reaction. Whereas with our dinitrogen tetroxide reaction, our forward reaction is endothermic, so we don't want more of that. We want more of the reverse direction, because that's our exothermic direction. So our dinitrogen tetroxide is going to shift to the left. And both of those changes favour the exothermic direction. There. So hopefully that's clear. That's dealt with Le Chatelier's principle in a bit more detail, and we've considered changes in concentration, pressure and temperature on the position of equilibrium. So finally, let's just check that we've got our learning objectives all okay. So the first learning objective was, do we know that many chemical reactions are reversible? Well, hopefully we do. We know that. And so next, do we know that in a reversible reaction at equilibrium, the forward and reverse reactions proceed at equal rates? Well, I think we do, because we did that chart of rate against time for forward and backward reactions. And do we know that in a reversible reaction at equilibrium, the concentrations remain constant, not necessarily the same? Reactants and products are not the same concentration, but they are not changing. And that follows, that point about the concentrations follows the point about the reaction rates. And also, are we able to use Le Chatelier's principle to predict qualitatively the effects of changes in temperature, pressure and concentration on the position of equilibrium? Well, we went through each of concentration first, then pressure, then temperature, and we did a table of all the changes in all the changes and what effect they would have on the positions of equilibrium. So with those three tables, we did that point there. And so lastly, do we know that a catalyst does not affect the position of equilibrium? Well, we do now, we've just read it. It doesn't affect the position of equilibrium. It doesn't affect the yield of a reaction. All it does is it allows you to get to that equilibrium position quicker. So if you didn't know it before, you know it now. And thank you very much for Le Chatelier's principle, and I'll see you in the next video lesson.